Okay, so speed is distance over time. All right. So, for example, when I say 30 miles, you guys should be writing this down. You don't have to redraw all this because on the you wrote that speed is ooh, what happened there? You guys wrote down that speed is equal to v is equal to the distance over time. So when we say 30 miles per 1 hour, that's what we mean. Okay. Any questions on that? So it's the distance over time. And V, does anybody in here want to take a guess at what V stands for? Velocity. Now in ICP, we don't make that big of a fuss about the difference between speed and velocity. But velocity, but we are going to a little bit. Velocity is a speed and a direction. Speed is just speed. So if I say I'm going 30 miles per hour, that's just a speed. But if I say I'm going 30 miles per hour northwest, that has a speed and a direction. And technically, it's a vector. Okay. So speed is equal to the distance versus time. But in a science class, because we're going to be doing science stuff, remember this is meters per second. So when we go to do our physics, for the t-shirt launcher, we have to convert all the units to meters, like all the lengths to meters, and all the time to seconds. Okay? Now the average speed, I don't know if you guys have learned this or remember this. If you have, that when you put a bar over something, that generally means average. So when we put a bar over a letter, that means the average of that. So V is speed, but V really means velocity. And then when we put a bar over it, we're saying average velocity. So the average velocity is the total distance over the total time. And the other thing that I want to highlight over here too is that when you graph the distance versus time, if you have the curve or the slope of the graph is your velocity, right? So let's write that down too. Slope of distance versus time is speed. Why does that keep doing that? That's bizarre. So, and that's going to be, it takes a little getting used to. But if you practice it, you can, and we'll do the motion sensors some more with like cars and tracks and stuff like that, and you'll see how motion works. And when we graph it, you'll see. Oh, remember with the t-shirt launcher, with the t-shirt drop lab, the graph went like this, and that's how we knew when the t-shirt was falling because the height was changing. It had a curve to it, not a big curve, but it had a curve to it, and that's how you can tell what the speed is doing. So a straight line means that it's a constant speed. A horizontal line that's parallel to this axis means that it's sitting still. There's no change in the distance over time. And then a wobbly, wavy line just means that the speed's changing. You could go up and you could go down. What does that mean? You're going further away over time or you're getting closer over time. Okay. Does everybody have this written down? All So now, this is an example. So remember that Isaac Newton, when he started doing this stuff, he was just measuring the distance something traveled over time. That was it. He was just measuring the distance something traveled over time. So what is the average speed of an object? Well, remember that it's the total distance. You should be writing this down. Over the total time. Because your homework's going to have something just like this. Okay? Now, remember that your answer has to be in meters per second. So what we need to do is when you look at this graph, it has like this little curve to it. So if you start at 0 time, it looks kind of like a straight line from here to here, right? Then from here to here, it's that flat horizontal line. What's that? Yeah, we're going to label all that. And then it goes in a, well, slightly different line. So let's do a slightly different color. This is a straight line, okay? So remember, straight line means a constant speed, so this is a constant speed. That's kind of hard to read. And this one means no speed. It's not moving. Sitting still. And this one here is a constant speed, but it's a slower speed. So this is constant. But it's slower than the green. Well, how do I know that it's slower? It's less steep. The slope is lower, right? So when you think of the slope, the steeper the slope, the faster the speed. Okay? But now for the average, they just want to know the total distance versus the total time. So if you look at this point here, by the way, we're used to seeing x comma y in our graphs, where normally this would be the x-axis and normally this would be the y-axis. But the reality of it is our x-axis is the time in seconds and the distance in meters. So if I look at this point here, this one here, I see that the coordinate for that is 10, right? Because we go over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the x direction. And then I go up 180. The time is in seconds, and the total distance is in meters. So then my total distance would be 180, and my total time would be 10 seconds. So because it's in meters and it's also in seconds, I don't have to do anything. Now that's the average. Because what's the total distance this thing traveled? Well, 180. And how long did it take to do it? 10 seconds. So if you do the math on that, what's 180 divided by 10? 18. So on average, whoever traveled this distance, they travel at about 18 meters per second. By the way, that's super duper fast. Okay? That's super duper fast. So you're actually going to have a problem like that on your homework. Okay? Does anybody need a little more time to write this down? I see a couple pencils still moving. Can I move on? All right, write this down. All right. So instantaneous speed is at that moment in time. So what I want you to do, this is where, so Isaac Newton graphed speed over time. Or I mean, not speed over time, distance over time. So he would make these graphs that look like this. And he noticed behavior that went like this. This is very frustrating. Why does it keep doing that? Okay? So that's really what it kind of looks like when something falls to the ground, if you study the behavior. Because when you let go of it, it's slow and it speeds up and it speeds up, so it drops faster and faster and faster. Okay? While he was trying to figure out how fast is it going right here, right? Well, he realized there's no easy way to determine how fast it was going. What he really needed was a slope. And so he came up with this very easy way. I think it's because I'm close to the top. He came up with this way to determine the slope by calculating, and it's what we call the tangent. But it's really calculus. He invented calculus or used calculus. Some say Leibniz invented calculus. Some say Newton did. I think they probably read each other's papers. But calculus allows you to find something at an exact moment in time, and that thing is instantaneous speed at that moment. Okay? And you could think of it like a speedometer. Really, your speedometer kind of takes an average, but it takes a very short average, which is what calculus does. Calculus actually calculates the slope between 2 points. So it'd be like this point and another point right next to it. Oops. It does not like me writing up there, which is very bizarre. Okay, well, we're going to leave it alone. No, we're not. We're going to try. And then he calculates the slope of between those 2 points. Oh. Can I do it? Yeah, there we go. But they're very close together. In fact, they're so close together, they're almost infinitely close together. The distance between them is theoretically like 1 over infinity. Thank you. All right. velocity has a speed and a direction. So we looked at this problem in our notes from the other day. I'm going to switch screens here momentarily. So let's do a couple of examples of that. So if I say, think of this think of one of these arrows representing 1 meter per second. Okay, you guys need to write this down. Think of one of these arrows as representing 1 meter per second. Let me write that a little better. That's a little sloppy. 1 meters per second. Okay, so now if I wanted to say to somebody, I'm going 3 meters per second, the only thing I need to do is kind of think of this in terms of creating 3 of these and putting them tip to tail. So you could think of it in terms of 3 meters per second would be an arrow that's 3 times longer. So I'd make one big arrow like this, and that would be 3 meters per second. Okay. And then let's say I want to make another vector. So another vector would be, I'll do 4. Is that 4? Yeah. So another vector would be 1, 2, 3, 4. Okay. And so this arrow, let's make it blue. No, wait. How do we do that? Over here, yeah. Let's make it blue. And then this arrow here, in order for it to be 4 meters, I have to have 4 of those unit ones. So I'm going to draw my one vector this long. Okay. Oops, wrong one. Let me move this out of the way. And then this one would be 4 meters. Oops, I want to change that color to red. So this would be 4. Oh, that's horrible. Oh no. So that would be 4 meters per second. So let's pretend I'm on a sailboat. Okay. Let's pretend I'm on a sailboat. Let's pretend I'm on a smaller sailboat. And I'm starting off right down here. Okay. And the wind is blowing this way. All right. What direction and speed will the boat go? Yes. Don't make fun of you. I won't. Yeah, it'll still go forward. And you think it'll slow down? You don't know. Okay. Anybody else want to get in on this action? All right, so here's what we're going to do. We're going to take one of these arrows and we're going to try to rotate it to point to we're going to try to rotate it so it's pointing towards, let me move this out of the way. So if I go 1, 2, will somebody get that door, please? 3, 4, okay? So it's actually going to go 5 units, it looks like. So it's going to go 5, whoops, wrong color. All right, there we go. 5 meters per second that direction. Does that make sense? So that's vector. That's vector mathematics. In fact, there really should only be one arrow, and I'll get rid of all these. But this arrow, so let's think of it like this now that we've counted it. Delete, 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 delete. Okay? That's really it. Does everybody have this written down? Same thing. I could replace this with an airplane and make it, 300 miles per hour in a wind that's 30 miles an hour. This is how you determine which way the airplane's going to fly. Which is, by the way, if you fly out to California, it takes about a half hour longer than it does for you to fly back here from California. Because the wind blows from the west coast towards the east coast. Did you guys know that? Yeah. So the airplane is basically flying out to California, in most cases, slower than it is on the way back. On the way back, the wind pushes the airplane and it can fly faster. Yep, true story. All right, here we go. We are almost done with our notes. And vectors, here's an example of what vectors are used for in the real world. So when they look at and they say that a hurricane has 50-mile-per-hour winds, they're actually measuring the wind, but meteorologists are actually looking at things like slope fields and things of that nature. But basically, those little arrows represent the direction the wind is blowing, and the longer the arrow is, the stronger the wind is blowing. The shorter the arrow is, the less it's blowing. So in this weather pattern here, you see this is really moving quite a bit. But out here, because the arrows are shorter, they're not really moving. And way over here, there's a wind that's moving around, but not really. But when you get right about here, see how long those arrows are? You don't have to write it down. And this is what I was talking about with regards. So this is, we're right here, right? And California is right here. And so this is the weather pattern. So when you fly from, let's say, Midway or O'Hare, and you fly this way to California, the wind is pushing against you right over here in the desert. And sometimes it pushes you this way too, pushes you down. But on the way back, if you fly out of LA and you fly back this way, it pushes up for quite a while. Then you have a little resistance here, and you fly back. And you can tell it's a little bit based on the arrows. Now over here, there's a lot of, and this is just a snapshot of one moment in time. Sometimes there's stronger winds, sometimes there's less. Here's another example of vectors being used to measure really anything. It could be force or pressure, fluidity, like the flow of a fluid. And then here's another one. You could see that these little arrows over here, these vectors over here are shorter, but over here they're much longer, right? And that's a measurement of wind. Here's another one of a hurricane that's going on. Or maybe a baby hurricane. I don't know, that's a pretty big hurricane. It's about half the size of Florida. And here are some weather patterns of the Earth. And so remember that if you add one vector plus another vector, it's the length gets increased to 2, just like we did in the last example. Okay? I'm going to do one more example for you guys, and then we'll give you your homework. So I mentioned that I, Mr. Adams, let's imagine, and remember this too, because this is like in your homework. How do you guys remember how to tell northeast, southwest, all that stuff? How do you do it? It's never eat shredded wheat. You said no? Well, what do you guys say to remember it? Anyways, you want to write this down because you have homework problems like this. Let's say I go 3 steps north, then I go 2 steps south, 4 steps east, 3 steps west. Where am I? So the easiest way to do these types of problems, and this is a short, simple problem, is you're just going to write it all out, sketch it out on a piece of paper. But this says I went actually, let me just delete all these. I went 3 steps. I'm going to make this shorter. 3 steps north. Then it says I went 2 steps south. So from there, I went this way. Then it says I went 4 steps east. Then it says I went 3 steps west. Where did I end up? So if you think about that, in terms of my original step, I started here, and I go up 1 and over 1, and I end up here. Right? Well, what would you call that if I were to measure it like this? It's actually a little bit more than 1 step. It would be, if you were to actually do the math, it'd be like 1.4 steps northeast. Okay? Yes? Yeah. Any questions? Okay, that's your homework for today. Now, how does this tie into the t-shirt launcher? Okay? Well, it's not your homework. I'm going to give you your homework. That's your notes for today. How does it play into the t-shirt launcher? Remember, we're going to take a t-shirt, and it's going to come out of a cannon, and it's going to go up in the air, and it's going to land over here and hit a target. But it's going to go up. It's also going to go to the right. There's also going to be gravity pulling it down, and we're going to measure all of this stuff using vectors. Okay? So I got to teach you vectors first. What's this thing pulling it down? Does anybody know? Gravity. an interesting eye. All right, let me turn this